Hello everybody, this is Andrew from Trick Cycle Turbine, trying to talk a little bit about how Trick Cycle Turbine is not going to have some of the same issues that Wankel or Liquid Piston has. We are not a rotary, we do not have elliptical mass. So my goal today is to talk about why that's important. Alright, you may have heard about Liquid Piston. They've been getting a whole bunch of different government contracts. They've had a really successful start engine raise. They've gone to do some other raises. They're claiming 30% more efficient off their engines. We do not buy it, and I'm here to explain why. So first of all, they did have a working mini engine. The Liquid Piston is essentially a reversed Wankel. I'll kind of explain a little diagram of that soon. But it doesn't fix what we view as the most important critical inherent flaw that the Wankel has, which is the slower cycling speed. And that's because of the elliptical mass. So just a quick comparison of the Liquid Piston engine versus the Wankel engine. Okay, so the Wankel was a triangle-shaped rotor in a peanut-shaped housing. This is a peanut-shaped rotor in a triangle housing. Now they did have a couple things here. They have the new HEHC cycle, which basically mixes in with the with an Atkinson. Driving for Answers did a really good video explaining how that is. I don't necessarily see it so easily from this view, but the main thing is you have static seals instead of rotating seals. The apex seals here is on the rotation part. You have a little bit better heat distribution in the housing. Now if you watch this, the same part of the peanut-shaped rotor has the exposure to explosion forces. So this is the hot side of the peanut-shaped rotor, and this is the cold side of the peanut-shaped rotor. In the Wankel engine, you have the rotor getting relatively even heat distribution because it's moving around, and the housing has a hot side and a cold side. So thermal heat distribution still has some issues. It's just where. What is changing with heat distribution? Okay, not necessarily the point. Point is it has this elliptical motion. Now I want to show you on this video where they're talking about it. The shaft speed is faster than the rotor speed, and it has to do that because of how they gear this with the elliptical shape motion. Now I'm going to speed up here and show you this eccentric that you have in the Wankel engine. Now, Liquid Piston is a little bit different. They've got a different looking shaft. Driving for Answers did a good video on this. They're actually breathing through the center shaft, but ultimately it's the same problem. You have this internal gear reduction where your rotor speed is slower than the output shaft. I've seen videos talking about how that's a good thing. That shows that you can get really high RPMs off your motor. Well, not really, because high RPMs is good in as much as it converts to high actual speed of the combustion events itself. Okay, so here's a graph of what I'm talking about. In 1080 degrees of rotation, the normal Otto cycle with a piston can get 3 combustion events in that degree of shaft rotation, and the Wankel can only get 2. So you have more time where the combustion event is exposed to the different metal parts of the engine and less where it's moving. That's really important because in the heat transfer equation, your delta time, the time available for your heat to transfer, is directly related to how much gets transferred. I mean, this is obvious when you're cooking something. Let's say you're baking a cake. The longer you have it in the oven, the more energy gets transferred to the cake, the more done the cake gets. You leave it in there too long, it gets burnt. When we're talking about an explosion that we want to turn into motion and not into heat, we do not want to have a large delta T. Okay? Wankel engines have around, this is saying 30% efficiency. Some of our other searches saying it's really more like 28% thermal efficiency. So only 28% or so of the energy in the gasoline or diesel or whatever fuel you're running turns into motion. This is lower, significantly lower than a piston engine. A normal Otto cycle can get close to 40. So that's a big difference. Here's an example of why we say the majority factor is the speed. Okay, Formula One engines have around 52% thermal efficiency. This is not normal for a engine. Of course, they do have $1 million budgets, but the main thing is they're running really fast, to like 11,000 RPM all the way up to almost 20,000 RPM fast, depending on the year and the engine, things like that. That is less time for your explosion event to become heat. Okay, here's another way to look at it. When you look at an efficiency versus load graph, the load is essentially the same as RPM, because the more load you put on the engine, the faster it needs to run to put that power out. So load is essentially RPM, which is saying the faster you run, the further you go across the load here, the more efficient the conversion is from chemical energy to work, discounting heat. So because of that, the Wankel, due to its slower cycling speed, wrong one, here. Due to the slower cycling speed of the Wankel, it will never compete with an Otto cycle. So the 30% efficient that they're claiming on their main site, they've got different things saying that the Wankel is more efficient. The only problem is compression ratio. We do not think that that is the case. Wankel engines have run almost up to 12 to 1. Normally they're running around 9 to 1. Standard pistons are around 10.5 to 1. Of course, unboosted on that. You can get pistons to whatever you want with boosting or different things. And the Wankel has variations too. But the compression ratio difference between a Wankel and a piston is not sufficient to justify the difference in efficiency. The main contributor is the combustion speed. And that's where we think you can't fix it when you have the elliptical mass. The internal reduction to get your elliptical rotation into a perfect turbine-like rotation, circular rotation, simply doesn't work well for efficiency. That shaft is the problem. This rotor shafts coupling, that is why there is problems. There's no way around it. So our turbine is direct. You do not have elliptical mass, so you are spinning in a circle. When we do our conversion, it's a direct drive. So there is no internal reduction. There is no slowing of the cycling speed. We can match the combustion speed, and in fact, because we we do some other different things, we actually go the other way. We go faster, but there is no inherent limitation from the elliptical mass that slows the cycling speed down. So ours is not a rotary. These rotary engines are inherently flawed, and they will never compete. Thanks for your time.